This conference will now be recorded.
Hi, good morning.
Good morning, Madhu.
Good morning, sir.
Good morning. So hope you are able to see my screen.
Yes, sir.
Yes, Madhu.
Okay. Okay. So fine. So let us start now. So yesterday we have completed our third step of our project, that is feature engineering. So we have completed all the 5 steps. We started with a little bit of our domain knowledge and engineered 2 interesting features. Then we applied interaction features kind of heuristics, and then again we engineered 2 more features, and then we looked more critically at all the sparse classes within our categorical features and cleaned up everything after taking a little bit of advice from some civil engineering friend. And then we converted all the text values that are existing in our categorical features. We have actually created dummy variables for them using those get dummies function. And so we have more columns have been created. And then finally what we did is that we have had a very critical look at all the features that are on the data set, and finally we removed 2 of the features, that is our transaction year and also the uh, built year, the property which year it was built. These 2 columns we have removed because from these 2 columns anyway we created another feature called property age. So after having done all that, we saved it as ABT, analytical base table. So this is the data set that we will use to train a set of regression algorithms and build a model that our customer wants from us. Okay, so before we start the process of model building, training using this data, a set of algorithms, so we will actually spend some time review some regression algorithms, because the task we are doing in this project is regression analysis. So we will review a set of regression algorithms. However, we started talking about these regression algorithms and did a little bit of work during our toy project, and we will continue the discussion. So today we'll have a little bit of more theoretical discussion only, but to build intuition into how each of these algorithms work, we will try some code also. Okay, keep that in mind. So again, intentionally, deliberately, I divided this step of selection of suitable regression algorithms as a step I have put, because in a project we will come to a situation where we have to take a pause, look at all the potential algorithms that are available to solve a particular kind of problem, and try to understand, build a little bit of intuition into them so that we will be able to use them in a better way. So that is the step where we are in. So we are going to take a pause and try to understand a set of good regression algorithms that may come handy for us as we solve this problem. Okay, so that is the step 4 we are. So in this, what we will do is that we will introduce you to 5 useful algorithms for regression task. Okay, again, when we get into our classification problem, we will review classification algorithms. When we get into our clustering problem solving, then we will look into clustering analysis algorithms. But right now, because we are solving regression, we will review 5 good regression algorithms. So first one is lasso regression, second one is ridge regression, third one is elastic net, and fourth one is random forests, and fifth one is boosted trees. These are the 5 algorithms we will use in our project. Okay, so if you look at the first 3 of them, are actually called regularized regression algorithms. Okay, what is regularized we will understand, but these are regularized regression algorithms. In fact, in our toy project we have used a simple linear regression algorithm, and then anyway we have used the same simple linear regression algorithm using a polynomial terms on our table. We also covered some polynomial linear regression, but fundamentally both of them we have used a single linear regression algorithm. Okay, in fact we imported from scikit-learn linear regression class and then we used it. We have not used lasso, we have not used ridge, we have not used elastic net in that project, but we'll be using regularized linear regularized regression algorithms. These are called regularized regression algorithms. Okay, so both all these three are actually just little bit of enhancements on top of your simple linear regression algorithm. Okay, they are some extensions or improvements on top of your simple linear regression algorithm. Okay, so what is that real enhancement or improvement? The simple linear regression algorithm, we are actually regularizing it. Okay, so to make it perform better. Okay, we will cover them, don't worry, you will understand all these terms. And then the last two algorithms are tree based algorithms. So here fundamentally we use mapping, mathematical mapping functions. Okay, and here we will use a tree based models, decision tree. Okay, decision tree. Okay, again we at the time of toy project we used a word called ensemble, meaning nothing but is grouping trees, creating more trees. So already we have used an algorithm on random forests. Okay, again there is another way of grouping, and based on that grouping we have another algorithm called boosted trees. But fundamentally random forests and boosted trees are decision tree based algorithms, and here we have used improvisation called regularized. Here we are using ensemble. Okay, that is another tactic to improve a simple decision tree based algorithm. Are you with me?
Yes, sir.
Okay, so these are effective in large part because they each have some form of automatic feature selection. Okay, yesterday I was talking to you, when you have on your data set lot of features, so as the number of features increase, meaning the dimensions are increasing. So when that happens, actually models will become more overfitted. Okay, so these algorithms, the five above algorithms, they have some mechanism of what we call automatic feature selection. In case there are too many features which will cause the model to be overfitted, they have internal mechanisms to reduce or shrink those features. Anyway, I am using that words, don't worry, everything you will understand in few minutes. Okay, so there is some form of automatic feature selection. In applied machine learning, individual algorithms should be swapped in and out depending on which performs best for the problem and dataset. So we have one model to be built. Okay, but we will not build that model with only one algorithm. Actually what we will do, all important algorithms whichever can solve this problem, we will build models using all of them. Again we will tune them also using a lot of hyperparameters, and so multiple models with multiple set of algorithms we will build, and we evaluate by testing it, measuring some metrics, and then decide which is the best. That is how in practical machine learning people build models. They don't build a model with only one algorithm. Okay, so they build models with multiple algorithms with multiple settings and check which one performs better using a set of metrics, and then decide which is the best model. So that is what we will do, because we are doing a practical machine learning course. We are not doing a theoretical machine learning course to understand a lot of internal details of how an algorithm is designed, how algorithms work. All that is important, but in this course we will not focus on that. We will focus deliberately on how to use them and build some practically working kind of models. Okay, so therefore in this module, whatever algorithm review we are doing, we will focus on intuition and practical benefits over math and theory. So we will not go into lot of maths. Little bit of maths has to be told, that only will tell. So lot of times for lot of people, when we start with a lot of math and also a lot of theory, actually it is boring also. So we are not going to do. But any way, I'm not telling that maths and theory are not important. They are important. But after having done some practical work, after having built some kind of intuition on how things are working, then based on what you want to know, you can go into the depth and understand. So a time will come for that kind of learning also. But in my opinion, this is not the time if you are first time learning machine learning. And hence deliberately I am not going to talk about lot of math and theory of algorithms that can be taught in another 100 to 200 hours actually. Anyway, we don't have that kind of time. Actually, more important, I too don't have that kind of knowledge. Okay, to be really frank. Okay, so are you with me?
Yes, sir.
Okay, so let's move on. So this again I divided into 5 steps. Maybe we'll do in whatever number of classes based on the size of the topic. So first we will uh, again go back to our toy project a little bit and bring that concept of model complexity, because that is the real issue in practical machine learning. The heart of machine learning is model complexity. And as we are building the real kind of projects now, earlier on we only built a toy project, but here we are dealing with a real data set with a real customer kind of situation. Then we will bring and review what is this model complexity and what are the practical techniques and tactics that we will put into place to fight against this issue called model complexity. And then as we are building the models, uh, we will understand each of those tactics very, very carefully and see the effect of the tactic. Okay, so that is why I will review again the model complexity issue in the first lesson. Then we will talk about what is this thing about regularization. Okay, we can go and talk a lot of mathematics here, but we will not do. We'll do it very, very simple way. And maybe again, to build intuition, we will do some coding work maybe tomorrow. Okay, then we will review the regularized regression algorithms, lasso algorithm, ridge algorithm, and elastic net. They fall under these regularized regression algorithms. So we will go through them quickly. What is that? And then we will uh, anyway apply them in our project. So we will have basic understanding of those three. Then tree-based algorithms are there. So tree-based algorithms use to fight against this model complexity. We ensemble methods will apply. Ensemble methods, when we talk something called bagging and boosting, are the techniques of grouping many trees into a group of trees and achieve some benefits. So there is a technique called bagging. That is how random forest regressor actually uses the bagging technique. And there is this gradient boosted tree, another algorithm, boosted tree algorithms they are called. that uses a principle of ensembling that is called boosting. We will not go into mathematics of all that. We will just talk about what is bagging, what is boosting, and what is generally ensemble methods. And then once you apply, again, ensemble is a very generalized term. You can talk about ensembles with deep learning algorithms also. Okay, regularization can be talked for deep learning algorithms also. These are concepts basically. When they are applied, the ensemble methods are applied on decision trees, then we call them tree ensembles. So this random forest regressor and boosted tree regressor, these two algorithms, they are tree ensemble algorithms. So we will review all of them and then move to final step of our project, where we apply all the algorithms that we learned quickly and build a practical process to do a factory way of training variety of models with variety of uh, hyperparameters. And though it appears very complex, but Python scikit has such useful functions. It makes your life very very easy. But we will use a industry proven way of building models in the fifth step. Okay, so these are the 5 steps in which I am breaking this reviewing of algorithms for this project. Okay, so let us go to the first step now. Okay, the heart of regression algorithms, heart of machine learning is model complexity. So I have kept on talking from almost early days of this course. Model complexity is the heart of machine learning. In fact, I used a word is that model complexity is the big boss of machine learning. What is big boss? Big boss is nothing but a big villain of machine learning. So like whenever you play computer games, we keep on playing against that villain. Okay, so as you move from one level to another level to another level, a new villain appears, and final level the real villain appears, and that person is called big boss. So who is the big boss for machine learning? Actually, we told earlier it is model complexity. I may change that little bit today, but let us review that again. So I'm telling, when I'm talking about model complexity, I came up with actually two terminologies. I talked about underfitting as well as another term called overfitting. Okay. So what we told is model complexity. To learn the data, if I give an algorithm lot of flexibility, then the algorithm will learn the signal and also some noise, random noise that might exist in the signal. So if you give too much flexibility, the algorithm, let's say the algorithm has too much flexibility by making it very complex, then it will learn not only the signal, but also it will learn the noise, and thus it might actually create an overfitted model. That's what I talked. And also we told, if I don't give through my algorithm lot of flexibility to learn from data, then the algorithm is will be creating a model that is underfit. Okay, so both terms we used, underfitting and overfitting. But now I'm telling underfitting is okay, because we that doesn't solve any problem. So if you have to really build a practically working model that it learns from some data and is able to predict for some new unseen data in a very generalized good manner, then an underfit model anyway will not be able to solve that. Only thing is that a model, first let it be very overfit, but if we can reduce the overfitting using some tactics and make it smoothen out the outputs, then maybe they are more useful. That's why right now here I'm talking about overfitting is the final boss of machine learning. Let us talk about it a little bit. So before we can get to the algorithms, we need to first cover a few key concepts. Okay, so I'm recapping only, already we covered them. In our first toy project, we introduced model complexity. Okay, even calling that model complexity as the heart of machine learning. So now in this discussion, we will go little deeper into practical challenge that arises from the model complexity, that is overfitting. Okay, so that is what we'll do. So review of model complexity. What is the definition of model complexity? We talked already. It is the inherent model complexity is also known as model flexibility. Okay, model complexity is a model's inherent freedom to represent complex relationships between input features and target variable. Okay, it has a lot of freedom by putting a lot of complex mapping functions or complex tree structures. Then it will learn everything in the data, and also it learns noise in the data. Then model complexity is too high and it produces overfitting. If we don't give any freedom, it doesn't have any flexibility to learn from data, not even signal, then it will tend to create an underfit model. So both sides, there is a problem. So model complexity definition is, model complexity is a model's inherent freedom to represent complex relationships between input features and target variables. That is how we defined model complexity. So we defined model complexity using other terminology also. Signal versus noise prism we have defined. So if a model, an algorithm actually recognize the signal and ignores noise, that is a good model. But if it is having too much flexibility to learn signal as well as noise, we tend to produce overfit model. If an algorithm cannot even recognize the signal, it tends to fit underfit model. That is how we define. And also we used another two terminology, or through another prism also we explained that in the early course. We talked about high variance, low bias, bias variance trade-off. So overfitting is around high variance, underfitting is around high bias. So we have to balance between that variance and bias to arrive at the right kind of complexity. That's also we talked. Hope you still remember. Again, all these kind of things are more important for those who want to go for interviews and get jobs in this space, because in interviews they might ask, and if you are ready to explain them well, you have a better chance of being selected. So that is why these are important. Then let us review what we did in our toy project. We illustrated this concept of model complexity by modeling a noisy sine wave. We created a set of values of x randomly, then we ran a sine function on that, and then we added some random noise to that, and then we created our actual y. This is the target variable, and x is our input feature. And using this mapping function, we created a set of data, and we pretended that we forgot about the data and then started building models of various degrees of complexity. So we started with a mean model, this black dotted line we plotted at that time. We used a simple mapping function called y hat equal to y bar. And then we told that this model, no matter how much data you have, unseen data, it will always predict only one thing. So the mean model was too simple, so it was underfit. That's what we told at the time. Then we made it a little bit more complex by using a complex or mathematical mapping function, not as simple as y hat equal to y bar, but we have used y hat equal to beta 0 plus beta 1 x, that y equal to mx plus c kind of mathematical mapping function. And using that linear regression algorithm, we learned the data and overlaid our model. Then we got this slanted black line, and we told, again, this is also an underfit model. It was too simple. No matter how much data you give to learn this, it will only learn only lines, straight lines slanted. It cannot learn anything else. So this is again an underfit model. Then what we did, we increased the complexity further by adding to our table a set of polynomial terms. Our table was simple x and y. Then what we did, I have added columns like x square, x cube means same value in the x has been squared and put here and cubed and put here, and then I went on. So basically, to increase complexity, what I did, I used the same linear regression model, but I changed my table. I added more features into my table, more input features to my column, and I deliberately chose the values to be polynomial values of x. Okay, so at that time, actually, I again ran the same linear regression model and fit my data. Then it learned more coefficients, and those coefficients are actually able to understand curvy relationship because the terms here are polynomial terms, square, cube, to the power 4, to the power 10 kind of thing. That is why it understood my curvy relationship in the data. And the third order polynomial regression was the right amount of complexity. Anyway, by seeing, we told that. But then during toy project, we also increased the complexity way further. So I put along with my x square, x cube, x to the power of 4, 5, 6, 7, 8, 9, 10, and my y. Okay. So I increased the complexity, not by the way of algorithm. I used the same simple linear regression algorithm to learn the data, but the data I changed by adding my new features, and those feature values I deliberately chose to be polynomial values of x. Okay, and because of that, when I learned the data, I have actually learned 10 coefficients, 10 betas here, and then I substituted for them for every x. Then I got new y values, y hat values. I plotted them. Then the model looked like this, and by seeing, we decided that the 10th order polynomial regression was too complex. So it was an overfit to our problem. So we ignored this. But then we could have kept increasing this to the power of till to the power of 100 also. Then it gets more and more complex, and it will start understanding noise and ignore the signal. That is what will happen. So they are not practically any advantage of those kind of models. That's what we realized by seeing, because it's a one-dimensional thing. We were able to do that. Then what we did in the toy project, we did not stop here. We changed the perspective itself. Okay, let me not really bother about this mathematical mapping function. Let me represent data, whatever tabular data that I have, x and y. Let me put it into a tree structure. And then we used a set of decision tree algorithms. So when we applied decision tree, unconstrained decision tree algorithm, then this is the model that has been created. So it has actually memorized all of our observations happily. So it is not only understood the signal, actually it has understood more the noise. Okay, so these models are not really practically any benefit. So the unconstrained decision tree was also too complex. So it was overfit. Then what we did to make this work, actually we started using some constraining by using max depth parameter or min leaf size parameter, and we improved this. Okay, this particular thing when we did it. Okay, so the challenge is that most machine learning problems will be much trickier than our toy project. Okay, the project that we are right now going to do is that it will be much more trickier. Why it is much more trickier? Now, what is the shape of our data set? It has 40 or 41, I don't know, I don't remember. 40 features.
42.
42. So
Yes, sir.
41 input features and one target variable. Okay, so basically, if we are using a mathematical mapping function and putting it y hat equal to, anyway, there will be some beta 0 y intercept, but linear regression function when we use for each of these 41, let's say 41 will be x1 to x41. Okay, then the mathematical mapping function will be beta 1 x1 input feature 1 plus beta 2 x2, my input feature 2, then beta 3, my input feature x3, on, so on and so. It will be beta 41 x41 is my mathematical function. When I give this data to a simple linear regression algorithm, what it does, it will actually start working, and it will learn from the data, and it will apply something called a cost function. We talked, cost function is nothing but uh, sum of squared errors. Okay, sum of squared errors. So it will keep on finding a line through this data, because there are so many x's are there. It is not only simple line, it is not two-dimensional, it is multi-dimensional. Now if you have to visualize this, it is a horizontal surface in front of you, and in that all these points are kind of oscillating. Through that oscillating points, a optimum surface has been figured out, and that optimum surface where the sum of squared errors is actually minimum. Okay, all algorithms will have something called a cost function. Okay, cost function for regression algorithms is sum of squared errors should be minimum. So it will look at the data, it will go through and calculate a lot of statistics, and finally decides on a particular surface through this horizontal surface, where all these points are oscillating. You have to visualize like that. In that, it chooses a particular surface. For that surface, out of infinite surfaces that are possible, for that particular surface, the sum of squared errors is minimum. What is really squared errors? So I have x, think about x as 1 only now, and then because it is a supervised learning, I have my actual y. Using this data, I trained. Okay, let us take simple linear regression. Let's say it's only x and y. Don't confuse yourself with 41 x's and 1 y. That is our problem. That is why I'm telling our project is a lot more trickier than simple thing that we are able to visualize. Okay, let us take simple thing only to explain one more time for you. So if it is only x and y and you are using simple linear regression, what happens? My mapping function will be y hat equal to beta 0 plus beta 1 x. Okay, so I have some values for x and y, actual y. So this is the data set I have. Okay, so y is my actual y. Okay, and y hat is my predicted y. Keep that in mind. So now I gave this data to my simple linear regression algorithm, and what it does immediately, let's say it stopped at a particular line, like I have a data like this. Okay, these are the data points here. So I gave this data set of x and y. This is x and this is y. I gave it to it. Then it started, let's say, first like a horizontal line. Then it calculated the sum of squared errors. Sum of squared errors is nothing but for this line, it calculated, let's say it started that line first. Okay, out of this data. Then for that line, it will calculate coefficients. Beta 0, let's say it is 0.5. And because this is a horizontal line, there is no slope. Okay, so it is, now what it does, sum of squared errors it calculates for this line. Sum of squared errors is nothing but, so here it puts y hat for the same x. It substitutes x value for every 5 values of x here. Okay, and using this beta 0, beta 1, so my beta 0 is 0.5 and my beta 1 is 0. So it substitutes and also substitutes x value and calculates a y hat value. This is my y hat. Let's say this x is actually 2 and y is actually 3. Now y hat will be something beta 0, 0.5 plus beta 1x. My beta 1 is 0. So y hat equal to 0, 0.5. Okay, so that is my y hat. This is y. Then it calculates sum of squared errors for all data points. What is sum of squared errors? First, let us do squared errors. Error is nothing but the difference between my actual y and my predicted y. That is my 3 and 5.5. That is my error. What is squared error? I square them. What is my sum of squared error? I do a sigma of, let's say I have 100 points, I equal to 1 to 100. Then anyway, I'll put here I. This is my cost function. So my cost function for a simple linear regression algorithm is that sigma I equal to 1 to n yi minus yi hat squared. I is my actual yi hat is my predicted y. Difference between them, squaring that and adding all the observations. That is my cost function. So all of my algorithms, they try to minimize this. So now it found that the sum of squared errors, if we calculate here for this line, I have to calculate all that. Let's say it is 20. It came. Okay, sum of squared. So it will not stop there. Then it will tilt a little bit. Okay, and it will stop here on this line. Okay, then again it will calculate my cost function using the same formula. Let's say it is now 8. Okay, then also it will not stop. Then it will put it like this. Okay, the third line I am writing now. Now it calculates. Now it has become 12. So now as you tilted that side, it was reducing, but you tilted further, it reduced, it started increasing. So now it will again adjust little bit between 8 and 12, and ultimately it will stop where any side movement is only increasing my sum of squared errors. Then it will finally stop at a particular point. That is why we are telling where it will stop where sum of squared errors is minimum. That is how our linear regression algorithms work. And there is a concept called gradient descent. Okay, that's what it will slope it, and then it will start slow. It will go very, very fast from 20 to 8 by adjusting the line. But when it becomes 8 and 9, then it will become very slow there and try to adjust, and finally arrives at the particular line where the cost function is the minimum. That is how linear regression algorithms are designed. Again, we are not going into details of those algorithms. I want you to basically understand that. But the problem that we are solving today is much more complex, because it is not two betas. When we give our data set abt.csv to a simple linear regression algorithm, it will calculate 41 betas. Okay, and then it substitutes all these 41 betas into each uh, row of observation, calculates this y hat, and it compares with the actual y. Okay, and finally it lands at a particular horizontal surface, cutting through these floating points in that surface, a surface that is having the minimum cost function, or minimum cost, or sum of squared errors is minimum. Are you with me?
Yes, sir.
Okay, so every type of algorithm always will be optimized with respect to one cost function. Okay, so we have to understand those cost functions. Sometimes some kind of algorithms will use partial differential equations, then the cost functions will be little different. So maths is involved, maths is important. Okay, don't undermine the importance of maths. Okay, but right now if we go into deep maths, we will never be able to come out and complete any project. That is why we chose this approach of practical machine learning or applied machine learning. Okay, then you decide once you reach a particular point how to learn deeply. Okay, because the depth is also important. Okay, so keep that in mind. So when I am telling math and theory are not so good, Really, I don't mean that. Math and theory are actually the basis for all these things. That is why better actually we build solid understanding of that, but at the right time. Okay, so with all this, a question comes in our mind. How do we systematically find the right level of model complexity? When it is so complex, how do I know what is the right level of model complexity? Okay, that question has to be addressed. So let us understand again complexity versus overfitting. So what we do in practical machine learning is that we allow more complexity first. We don't try to start with an underfit model. We actually try to start with an overfit model, because at least they are capturing the essence of our signal also better than this high bias algorithms. So we always allow more complexity, but then if it is overfit because of lot of complexity, they are useless. That is why we allow that, but then we apply lot of safeguards against overfitting. So as a machine learning engineer, you have to understand what are those safeguards, conceptually what are they, and how to apply them, because that is what you have to really, that is how practical models will be built. We intentionally allow them more complexity, but we apply a set of tactics to fight against that overfitting that is caused because of complexity. So are you there with me? Can I move on? Any questions? Any questions from anyone?
We can move on, Madhu.
Okay. Okay. So what we are saying is that too simple kind of models have limited potential. So we used a simple linear regression model to understand this data. Then no matter how much data you give and train, it will only understand the data as straight slanted lines, nothing beyond that, because that is the inherent flexibility of that algorithm to learn data. Okay, so too simple, limited potential, but actually make it more complex, you have more potential. Okay, but problem is that they are overfit, but by applying some constraints we can smoothen out, and like whatever we did in our decision trees, max depth, hyperparameter, min leaf size, we have smoothen out a lot of this noise also. So more complex is more potential, definitely, but with safeguards like your hyperparameters and many other safeguards are there. We'll talk about regularization and all. So what we are right now saying that overfitting is the final boss of machine learning. Okay, not underfitting. So earlier we generally told model complexity is the final big boss of ML, but today I am telling overfitting is the big boss, because underfitting anyway doesn't solve any problem, but to build any good practical model we have to use complex algorithms. Intentionally we have to make it complex, but then we have to systematically smooth the output using some tactics. Okay, so overfitting is the final big boss. So the two main ways, so whatever you have, how do I increase complexity of a model? So far what we have done in our toy project, first we used a simple linear regression, but to increase complexity what we did, we added more features into the table. So we added features, polynomial terms we have used, and made it intentionally complex, and figured out of all the number of features that I can increase up to x3 x cube, actually it is understanding better. That is what we did. So one way of increasing complexity is adding more columns. So adding more columns will increase complexity. Keep that in mind. That is what we did in our toy project when we came to polynomial linear regression. Okay, another way to increase complexity is change the structure itself. Okay, here we are using a mathematical mapping function. I want to, this is useless for me, so how do I increase the complexity? So I change it to a tree structure. I did not use, because whatever this even polynomial regression also doesn't understand naturally the non-linear relationship that might exist between my input features and the my predicted variable. So that is why we change the structure. This is one other way to increase my complexity. And then we used the tactics to smoothen the things. So both of these can lead to overfitting, because you are intentionally increasing the complexity of the model. Both of these can lead to overfitting. Okay, so but first, choosing the right algorithm can also help prevent overfitting. Okay, so many tactics are there to reduce or fight against overfitting, but then one first step is choose the right algorithms. Then you can fight against your problem of overfitting. Okay, so that, so again, quick review of whatever we talked in the toy example. Finding the best model was very pretty straightforward, but real world machine learning is much more nuanced. Okay, because it is real, that is artificial. Okay, to start, we usually can't simply plot models and use an eyeball test to pick the best. So first thing is that visualization itself is tough. What is happening, uh, we cannot even visualize once the dimensions increase. Now we have 41 x's, and how do I visualize that? It requires very strong brain to really visualize that. I don't think, actually I don't have that kind of power to visualize that. So it gets more tough now. In the toy example, we had only one input feature. In the real world, we'll have many input features. That is why also we have to uh, understand these tactics and conceptually better, and why something is happening, why something will happen, why something will not happen, kind of thing. Okay, so how to find the right amount of complexity then in this given complex situation? So it is typically better to allow more complexity in your models intentionally, and then implement other safeguards against overfitting. Okay, so the reason is that if your models are too simple, they cannot learn complex patterns no matter how much data you collect. So they are useless if they are too simple. That's why we don't start from the side of the simple and slowly make complex. That is not a right approach. Make it complex and come backwards and achieve an optimum point. That is the better approach to build practical machine learning. Okay. However, if your models are more complex, you can use easy to implement tactics to avoid overfitting. In addition, collecting more data will naturally reduce the chance of overfitting. So more observations are there, then actually it is always good. More data is always good for model complexities problem. Okay. The bottom line is that because of that, okay, uh, we consider overfitting is the final boss, because the way we have to build this of machine learning, not underfitting. Okay, so though earlier on I told model complexity is the big boss, today I'm saying overfitting is the big boss of machine learning. Okay, so how do we defeat this big boss, the final boss? Okay, there are tactics. Overfitting is a dangerous mistake that causes your model to memorize the training data instead of the true underlying pattern. That's what we have observed. So this prevents the model from being generalizable to new unseen data. Okay, maybe let me put it here. What is this problem in a simple terms? Okay, let me just give me a minute. I want. Okay, I'm using a little bit different thing. Let us say I have, anyway, we talked about sometime. Let me select a pen. I have, okay, on the x-axis, I have weight of some mouse or mice. Okay. Then on the y-axis, I have length. Okay. Now I have a set of data points. Okay. Let's say I'll put here one data point, another data point here. Okay. I put it in black. I'm putting few more data points in red. So I have 7 mice. I put my weight and length. I measured them and did a scatter plot. Okay. The black dots, let me put back my black again. My black dots are actually the only 2 data points I have to train a model. Okay. So using this fewer observations, okay, very few observations, I created a linear model, because anyway it is a x and y, and the pattern also is looking like some linear relationship is there. So I applied a simple linear regression model, and because of that, it has how does a linear regression model work? It works with a cost function of sigma I equal to 1 to n yi minus yi hat squared wherever it is minimum. It stops there. Okay. So it aims to minimize the cost function, that is sum of squared errors, and it will stop there and fit a line. Let's say because it was having only 2 data points, it could actually figure out a line that actually overlaps these 2 points. This is my LM1, let's say linear regression model 1 I created. Now my red dots are my training points, testing points. These are the things I want to, this is the unseen new data. I want to use this black line to predict for these things. So this on my training data, on my trained data, what will be my sum of squared errors, that for that a line that actually uh, overlapping both the points. It is the sum of squared errors will be 0. It is not only minimum, it will be 0 for this line. Okay, it's perfect model for that way. But then what will happen to your unseen new points? Will it predict accurately? It is very good for your training set. But when you use unseen data, will it be same? Will it be that great? In fact, what will happen if we do the sum of squared errors for these points? Let me use this blue. Okay. For these unseen points, this is the difference, the distance between this is my y. If you put it here, this is my actual y, and if I use my prediction model, this is my y hat. So the differences are very high, the errors are very high for the new unseen data. So what this model has done, because we trained with fewer set of things, and because of this cost function is to minimize sum of squared errors, it shows the right point as per the algorithm. But this model will not be good on unseen data. It is not going to be perfect. It will have huge error. How do I make a line that actually it's okay, little not so good, not perfect 0, but some some of the squared error actually is not that minimum, little higher only. But if I do that, it will do for unseen data better. So if that is the case, what I will do typically, I will tilt this line a little bit intentionally. Let's say I use a line like this, okay, as my LM2. Okay, this line is not the sum of squared errors for the training is actually more, but for the unseen data, this new line, LM2 line, will be much better. It will generalize the unseen data in a much better way. So this black line that we have drawn earlier with less type of training data, it is an overfit model. So we have to apply some tactics to actually reduce that overfitting and make it more generalizable. So any model which is perfect on training, not so perfect on unseen and new data, that is an overfit model. So we have to adjust that. So that is what my black line, I adjust tilted little bit. How do I tilt? I have to apply some tactics to tilt. So those kind of tactics only are called regularization tactic, okay, or even your ensembling tactic. These are all tactics to do that. And then use train test splits and also something called cross validation. All those concepts will help you to adjust these issues and make from overfit to more generalizable kind of model. Are you there with me?
Yes, sir.
Okay. Okay. So while we are here, I'm telling, so overfitting is a dangerous mistake that causes your model to memorize the training data, okay, instead of the true underlying pattern. This prevents the model from being generalizable to new unseen data. Okay, if it is overfit to your training data, it will become less generalizable for new unseen data. Okay, so a good model is somewhere in between. Okay, so what are the various tactics to avoid overfitting? We use a technique called regularization, a technique called ensembling. Okay, then train test split is another tactic. Then we have cross validation. All these things we will learn now. And anyway, we'll try to understand regularized regression. What is this ensembling? Already the decision trees we have seen. Okay, then uh, at the time of model training, we will bring how do we use this data that we have to very intelligently do a split between how much data I will use for train, what data I will use for test, and using something called cross validation. Okay, don't worry, we'll talk about them, all these, but these are the various tactics to avoid overfitting. Okay, so picking the right algorithms also can prevent overfitting. On top of that, apply this regularization. Like now we have talked about lasso. Okay, then we talked about ridge, we talked about elastic net algorithms. Those are all actually regularized regression algorithms. We talked about random forest, and we talked about gradient boosted trees, gradient boosted trees. They are ensembled tree models. So we will learn all of them. Okay. So there are two main ways models can become too complex, leading to overfitting. Anyway, I'm repeating only. So basically, inherent structure of the different algorithms, number of input features. So like structure, decision trees, using them, we can make them more complex and then systematically bring it down. Or polynomial terms also increase complexity, then we can reduce by using some of the tactics. Similarly, adding more number of features also will cause model to get complex. So we use that. So that is where our step number 1 ends. Okay, now going back to this, we talk actually about regularization as the next topic. So what is regularization? Maybe we'll cover tomorrow, But let me go back to whatever again. Where is my, okay. So as we told in this example, LM1, okay, is a model which overlapped all the training points, training set. Okay, to make it generalizable, I told that we will use this kind of tilt a line little bit this side. So how do I make that line tilt a little bit? To do that, I have to adjust my cost functions. This is the simple cost function that black line has used. But to create a tilt in that line, I have to modify my cost function. I have to add some penalty factors to whatever this cost function, and also some tunable factor, like we'll talk about tomorrow. But that whole process is called regularization. Okay, you can artificially apply some other terms on top of your algorithm's cost function, and uh, you will not let the algorithm to learn even fewer data points are there, uh, that it will be zero minimum. Okay, it will be little bit more than that only, so that it may be inaccurate on the training, but it will be more generalizable for new and unseen data, and that concept is called regularization. So there are three types of, actually there are two types of regularization, or penalty. L1 penalty is called L1 regularization and L2 regularization, and use both L1 and L2 in a ratio, then we get another kind of algorithm. So this algorithm is called lasso algorithm, and this algorithm is called ridge. Okay, and there is L1, L2, both we'll use, and that we call it as elastic net. So when we did our toy project, we did not use these algorithms. We have used decision tree, but we have not used on our data these algorithms. So what we will do is that tomorrow we'll try to understand what is this regularization and apply on some, we build intuition using our own data set, synthetic data set, and apply these lasso, ridge, elastic net, and see what happens actually behind the scenes. So to build a little bit of intuition. So you have any questions?
Yes, sir, Ramshankar here.
Yeah, tell me.
Sir, here in this case, we had got LM1 as our model, which was perfectly fine
Yeah, yeah,
with zero.
yeah.
Now, sir, what will guide us to apply regularization on this model? Because the unseen data is unknown. So how do we?
Yeah,
Yeah.
yeah, unseen data is unknown, but when you see on your training data, when you see this difference between yi minus yi hat, let's say we used a metric earlier, that is mean squared error. Okay, what we did is that this sigma divided by n we did. Okay, here we are using sum of squared errors to minimize as a cost function, but as a metric we have used mean squared error. Okay, so when you do this black line and you look at mean squared error, it will be 0. Okay, agreed?
Yes, sir.
Okay, and any on your training data, when MSE is 0, meaning it's a overfit model, it started memorizing. So anything unseen data, because we have unseen, okay, it will not be able to generalize very well. The error will be, MSE will be far more higher on unseen data. Okay, it will be much more greater than what you have seen, meaning when you have that kind of situation, okay, your model is an overfit model. So you will know, first you will create this model, okay, unregularized, then you predict using this unseen data, calculate this MSC, MSc with training data is very good, but MSc with unseen data is very bad, meaning already you have overfitted your model. Then you have to apply some regularization.
Yes, sir, got it. Thank you.
Okay. Any other questions? Okay. So if you people don't have any other questions, so I'll stop here. In fact, I thought I will do both of the lectures today, but we went slow. It's already 5 minutes past 10. So we'll close here. So tomorrow we'll meet. We will understand the next step, that is regularized regression. And then maybe we play with a little bit of code to build intuition. Okay. So that's what we'll do. So let us close here. And thank you so much for your attention. See you tomorrow.
Thank you.
Thank you, sir.